Hi class, welcome to the next section. We're going to talk about inverse functions today. So I kind of separate things in this course as functions and their inverses. You'll see this later on when we talk about more calculus level stuff as well, because it's important to understand that inverses are generally functions themselves and how they relate to our functions. Okay, so first and foremost, we want to talk about what a one-to-one function is. A one-to-one function is a function that passes what is called the horizontal line test. So just like the vertical line test is a test to see whether or not a function is a function, a horizontal line test tests whether or not something is one-to-one. One-to-one means that every output has only one input, right? So the definition of a function is that each input goes to only one output. One-to-one function means that outputs also have a unique input that goes to it. Okay, so one-to-one function is a function such that every input has its own unique output. Okay, and the key here is unique. So that means that I will not have two different things to plug in that'll give me the same thing out. Okay, so if we go back to our vending machine example from the first video that we had for this section, I was talking about, if you press the root beer button, that you should always get out root beer from your vending machine. So to relate it to that example, I should only have one root beer button. Okay, so in my vending machine, there should not be more than one root beer button. So every button is different, basically. Okay, so if my two inputs are not the same, they will not have the same output ever, right? So an example of a function that's not one-to-one is the x squared function, because I can plug in a positive value to get out an output, and that same output can be reached if I plug in the negative value of that same value. So here my example is 2. If I plug in 2, I get out 4. If I plug in negative 2, I also get out 4. So x squared is a function. It passes the vertical line test, but it is not one-to-one because there are two different things I can plug in to get the same thing out. Okay, so it is not a one-to-one function. So again, I can tell if something is one-to-one by the horizontal line test. So I know I skipped over this very quickly, but you can read this in your readers, basically saying if I can draw a horizontal line and it hits my graph in more than one place, it's not one-to-one. So here, right, this is my function, some sort of parabola. This is the easiest example. If I draw a horizontal line, notice it hits my function twice. Okay, if this continues to wave in some form and hits it more than twice, that's also not one-to-one. So if I draw a horizontal line anywhere on my graph, it should only hit the function once. Okay, if it doesn't, it's not one-to-one. So inverse function. An inverse function is, what I like to think about it is like the easiest example, I guess. Let's go to an anecdotal example instead. When you come home from a long day and you take off your shoes and you take your socks off and your socks kind of pull inside out, that's an inverse function. Okay, that's an example of how we try to find a closed form for an inverse function. Is we're basically pulling our function inside out. Technically speaking, what an inverse function is a function will send your inputs to an output. You go from your domain to your range. An inverse function goes from your range to your domain. It's like a return flight, right? If you get on a plane and you go from San Francisco to New York, that would be your function. The inverse would be the plane that brings you from New York back to San Francisco. It's the return flight. It takes your outputs and it brings you back to your inputs. An inverse function only exists if your function is one-to-one. Okay, because if your function is not one-to-one, then you'll have several functions for your inverse, right? So since you won't have just one function, it's not an actual invertible function. Okay, the notation for an inverse function is f to the negative 1 of x. We call this f inverse. This is not a reciprocal. This is not a negative power. Okay, this is being applied to the function. It's different than say, an inverse or a negative exponent. Okay. What f inverse does is it takes your outputs of your function and it uses them as inputs and it brings you back, right? So your domain of your inverse function is actually the range of your original function, okay? And the range, the outputs, the set of all outputs of your inverse is actually the set of all the inputs of your original function, okay? So again, here I use that plain example instead of San Francisco to New York, I'm saying Oakland to Miami, right? It's the same kind of deal. So if I plug in a to my function and get out b, then for my inverse function, I would plug in b and get out a. Okay, so it takes my outputs as inputs, and the outputs of my inverse function is actually the inputs that they're associated with. Okay, so in general, if I take the inverse function of a regular function or the function of my inverse, they basically cancel each other out, and I just get my input. Okay, so if we have a graph, kind of like our composition graph here, where we start with our domain and our range, or a collection of all inputs and our collection of all outputs. Our function takes us from our domain to our range, and our inverse function then treats the range of our function as the domain, and it treats the domain of our function as the range. Okay, so f inverse takes us from the range of f back to the domain of f. Right, so the domain for f inverse is the range of f. The range of f inverse is the domain of f. Right, so it's like I said, like a return flag. Okay, so now let's talk about how to graph f inverse. So we're really just using this idea of that if I plug in a and I get out b, right, as a point on my graph, it would be ab. For f inverse, my input is b and my output is a. So a point on f inverse is BA. So a point on f is AB, on f inverse is BA. Basically what we do is we just swap the positions, right? It makes it really, really easy to graph these. So XY is an ordered pair for my function, then YX is the ordered pair for my inverse. Okay, so I just switch my values and I graph. So if this is my function for x, or I'm sorry, f of x, -2, 1, -1, 3, 0, 6, 1, 10, 2, 15. For f inverse, I'm just swapping the columns. My x's now will turn into the y's, and my y's will turn into the x's, right? So for f inverse, I just swap the order. Okay, it makes it really, really easy to graph. So symmetry-wise, I'm really reflecting f of x over the line y equals x. Okay, and so if I just reflect this, either I look at all the points and I switch their order, or I swap their location, because that's what's happening. My x's, right, let's look at this, oops, okay, my x's now are going to equal y's, right? What was x here is now y's. What was y's here now equal x's. So the line of symmetry is y equals x. So if I plot my graph, f of x, okay, this is not the same graph here. This is a different graph, right? There is no negatives here. This is just a generic example. If this is a graph of f of x, this would be the graph of f inverse of x. It's being reflected across the line y equals x. So the point that they share in common is the same point where f of x crosses the line y equals x. Okay, that's the point that they have in common for f of x and f inverse. So you're just flipping one across this line. You're swapping their ordered pairs. Okay. Now let's talk about how we find f inverse of x in terms of a function, right? Using function notation. So like I said earlier, you know, when you come home from a long day, you take your shoes off and you pull off your socks. Generally, your socks will flip inside out, right? Unless you do some weird stuff and you take them off normal, which I would think most people don't, right? They just want to take their socks off and they kind of flip inside out. That's what we're doing, okay? We are going to kind of hold on to the input of our function and we're going to isolate it. We're going to move everything else over to the other side of the equation. So our input value gets isolated. So instead of solving for y, right, isolating y equals something, like we normally would for a function, we're going to isolate x. We're going to say x equals everything else, and that is what the form of our inverse function will look like. So in order to ease that, to make it a little bit more natural for us in the way that we solve for our functions, we're going to swap out our x's and y's because we know, again, y equals x, right? So what we're going to do is we're going to make the substitution. We're going to say, instead of f of x equals something, let's just call it y. Okay, so we'll go back to the land of y equals some function, right? So we're going to say y equals our function. Then we're going to make out the substitution x equals y, meaning that everywhere I see y, I'm going to call it x. And everywhere I used to see x, I'm going to call it y. So I'm swapping my variables. All my x's turn into y's, all my y's turn into x's. So now I'm going to solve for my new values of y, which used to be my inputs, right? So I'm going to, just to keep it simple to us, since we're used to solving for y's, right? Isolating y equals this is my function. That's what we're going to do. Y will become x will become y, and let's just solve for y. Okay, once we have y isolated, we'll replace y with f inverse of x. Okay, so a lot of this is just us swapping out notation so that it's familiar with something that we've done before in our past in algebra pre-calculus. Okay, but really what we're doing is we're solving for the input variable. Whatever the input variable is, we're trying to isolate that. Even if it shows up more than once, the goal is to get it to only show up once and get everything else on the other side of the equal sign. Okay, so like I said before, I think about this as turning the function inside out. So let's do an example. So let's say I have f of x is 1/2 square root x minus 3 plus 2. Basically, I want to solve for x. But in order to keep the notation similar to what I'm used to, I'm going to call this y. Okay, so I'll call it y is 1/2 square root x minus 3 minus 2. And then I'll swap these out. So this will be x and this will be y. So now I can just solve for y again. So I have it in my standard notation where y is the output variable and x is the input variable, right? But really what I'm doing is solving for that input, which is now my y. So I'm going to solve for y. I'm going to add 2. I'm then going to multiply by 2 and then square everything and then add 3, right? It's just a typical way of solving for a function. We're really undoing PEMDAS and opposite order of stuff, right? So see it multiply, so I add. Okay, the next thing after I'm adding or subtracting is multiplication, right? Undoing PEMDAS. So addition, subtraction first, then multiplication, division, then exponents. So I'm going to multiply, then I'm going to square everything. I don't actually have to square it out. I can just keep it in this notation. And then I'm going to add 3. So I have my y isolated, and now y becomes f inverse. I basically took in my input, and I moved everything else to the other side. And that's my inverse function. So I had a square root here. Here, my inverse function is a quadratic. Okay. So let's do another example. Let's find f inverse for this quadratic. What I want you to notice is we've already talked about this. Quadratics are not one-to-one. They do not have inverse functions. So what happens when we try to find this inverse? Okay. I'm going to replace f of x with y. Swap out my x and y's. Okay. Isolate my y's. So I'll subtract 2 and then multiply by 2. Notice I can't get y alone, but you're probably saying, yeah, you can't, Professor Williams, just square root everything. Okay. So what happens then is I have plus or minus square root 2 times x minus 2. This is two functions. It is not one function, right? It's the positive form and the negative form. Right? This is not an actual answer. Well, it's an answer, but it's not technically correct, right? I cannot define this inverse explicitly, meaning as a single function. Okay? I'd have to kind of keep it as y squared equals 2x minus 2. This is called an implicit function because I cannot explicitly say y equals this, right? Because it doesn't work that way. So if I want to demonstrate this, if I want to kind of like graph this thing, I actually have to express it as two separate functions. The first function being the positive form and the second function being the negative form, right? I cannot express this as a single function. I cannot explicitly express it, right? So it is not a one-to-one function. It is not an invertible function, okay? Because I cannot express it as a single function. So here is my f of x, okay? I don't know why I didn't put this first arrow on it, but it's okay. So my inverse function is then the positive form, f1, okay? And the secondary form, which is the negative of that. And notice that this does not pass the vertical line test, okay? Oops. It does not pass the vertical line test, but it is reflected across this line of symmetry. But it is not technically a function because vertical line test, right? So there we go. Okay, let's do another example. So let's say we have a table of values. Okay, table of values is nice because it makes composition of values easy to understand, and inverse function is pretty easy as well. Okay, so let's go ahead and use this and talk about a mixture of compositions with inverses. Okay, so for composition of functions, remember we start with the closest function first, and then we make our way backwards, right? So I do have the answers written out, but first let's talk about this one at a time. So the first thing I want to look at is h of 1, right? So I go to x being 1, and I go down to the intersection with h, right? So h of 1 is 2. What I do then is I use the inverse for that, okay? So I'm plugging in 2 into f inverse, which means that I'm looking for what has an output of 2 for x, right? So before I'm plugging in x is 1 into h. Now, since I'm in an inverse function, I need to do the opposite. I'm looking for what has an output of 2 for f. Okay, so I go to f of x, 2. It has an output of 2 when x is 1. Okay, so f inverse of 2, that's what I'm plugging into f inverse, gives me an output of 1. So now I'm going to plug that into g. So again, I'm going to 1, and I'm looking what happens when I plug 1 into g, and I get out 0. So that means when I plug 1 into h, that into f inverse, and that into g, my final value I get is 0. Okay, so here, this composition means I'm plugging in 1 into h, that into f inverse, that into g, and I get out the value 0. Okay. Next, we have even more inverses here, so we're going to plug 2 into f, that into h inverse, and then that into g inverse. So first I start with 2, I go to its intersection with f, and I get out 4. Okay. Now I look at h inverse, and I'm saying, when do I get out 4? Well, that's when I have an input of -1. Okay. So now I go, when does g inverse, when I plug -1 into g inverse, well, that means I go to g, and I'm saying, when am I getting out -1? Well, look, I have two different values. I have at -1 and I have at 2, which means that this is not an invertible function. I have two different values out. So the inverse is not an actual function, which means it's not invertible. Okay, so there is no actual answer. You know, if I did ask you this, I would expect you to say g inverse is not invertible. Or if you gave me both answers out, I'd accept that as an answer. I wouldn't ding you for that because you actually gave me, you know, an answer for that's true. But the function is not invertible. Okay,